So we'll continue with simple harmonic motion today. So quick recap of what we had learned about simple harmonic motion. Last lecture, we had seen that it is an oscillation along a straight line. That is, it's a one-dimensional oscillation such that the displacement from the mean position is a harmonic, or another word for that is sinusoidal function of time. So the general equation was given by this. Where A is the amplitude, so that is the maximum displacement. Okay. And omega is called the angular frequency. That is how it is related to frequency or time period. Okay. And phi is called the phase constant or initial phase. Okay. So this, in a sense, was the definition of simple harmonic motion. Okay, so in general, we had also seen that the graphical representation of the displacement versus time will look like a sine curve. Varies between plus A minus A time period which value, okay, given by this. Okay. Now from this we had seen that the velocity is A omega cos omega t plus phi, and acceleration so from this we learn that velocity has a maximum magnitude of A omega, okay, and the velocity has 5/2 phase difference. with respect to displacement. And from this we learn that the maximum acceleration has a magnitude of a omega square, and acceleration has pi phase difference with respect to x. So comparing this equation with the displacement equation, we also get the relation that d2x by dt square, or acceleration, is minus omega square x. This also becomes an important relation for us. Which in turn means that the net force this is called the dynamical condition for SHA. Okay, so these are some of the things that we are going to be working on in the numerical applications when we see today. Just make sure that these basics up to this point are clear. Please go through this once and let me know in case of any doubt. Okay, let's move on. Now, next thing very important for us, the amplitude and the phase constant from initial conditions. So what do we mean by initial conditions? Let's understand. X is equal to a sine omega t plus phi, and v is equal to a omega cos omega t plus phi. So this means that at time t equal to 0, the value of x is going to be a sine phi. Just substitute t equal to 0 in the first equation, and the value of velocity, let's say v naught, is going to be a omega cos phi. Substitute t equal to 0 in this. Okay, so x naught and v naught, they are the initial position and velocity, and therefore collectively we say that they are the initial conditions, the initial condition from which the motion starts. or you can say state, initial conditions or initial state. So now from this, you can see that from equation 1 and 2, we use this relation that sine square phi plus cos square phi is equal to 1. See, x naught upon a whole square plus v naught upon a omega whole square is equal to 1. So this can be further solved to show that, let's take the a square on that side. Okay. And this gives us a first important relation, that amplitude, how it depends on the initial conditions. So for example, if we have a situation that a particle is in SHM with time period equal to, let us say, 10 seconds. If initially it starts from find its amplitude. So for this type of question, we will use the above formula. Okay. So just make a note of this and work out this question. We will discuss. Okay, so people, first of all, hope this equation is clear how it has come. Okay. So this is something very important to remember. The relationship between amplitude and the initial state, that is the initial displacement and initial velocity in an SHM. So let's understand this question now. In this, see, time period is given to us as 10 seconds. Okay. So from this we will get the value of omega. Okay, so that is so approximately So now our amplitude make this in centimeters instead of millimeters. So V naught by omega will become 2 upon 0.6. I'll approximate this as. This will be in centimeters. Okay, so this is our amplitude. So that is the relationship between amplitude and the initial conditions. Now the other thing is the phase constant. So we'll come to that. But just note this down first and let me know if there's any doubt. Okay, so Rahil, your question, yes, amplitude omega and phi, they are constants, that's true. So in the relation that we have, x is equal to a sine omega t plus phi, x is the dependent variable, time is the independent variable, all other terms are constant. And same goes for the relation of v and omega and all that. Okay, v is equal to a sine a omega cos omega t plus phi. So that same relation holds. Okay, omega a and all that are constants. So next thing we'll see is the phase constant, how that depends on the initial conditions phi. So we had the relation x naught was a sine phi. This was the equation one we had written, and v naught was a omega cos phi. This was the second equation. So if we just divide the two equations, you'll see that x naught by v naught is equal to tan phi by omega, or phi is equal to tan inverse of x naught into omega by v naught. So this is the phase constant. So let's look at an example now. An SHM has omega directly, let's say, equal to 10 radians per second. And at t equal to 0, x naught is equal to, let's say, plus 6 centimeters, and v naught is equal to minus of okay, find its amplitude and phase constant, and write the equation of SHM and plot its graph, that is x versus t. Now this last part, plotting the graph, is a slightly advanced type of question, not so much applicable directly for your NEET level of exam, but finding phase constant amplitude, that's definitely within your medical entrance exam level. So you should also just understand how to write the equation and plot the graph, just from a pure understanding point of view. That's why I've added those two questions. So just try this out, people. We'll discuss. Okay, anybody got the answer for this? It's basically just formula based. Yes, very good. So 6 centimeters will be the amplitude. No, not 6 centimeters. V naught by omega is how much? Minus of 0.6 root 3 by 10. And this is in meters per second divided by radians per second. So this is minus 0.06 root 3 in meters. So that is minus 6 root 3 centimeters. So this is, we use this formula. Okay. You'll see it will be 12 centimeters. The amplitude is 12 centimeters. Just take care of the units. I think all of you are making the mistake with the units. When we substitute this thing, that A is equal to square root of x naught square plus V naught square by omega square. These must be in same units. Okay. X naught must be the same unit as V naught by omega. So you have to convert. Either you have to convert x naught to meters or V naught by omega to centimeters. So that is what I've done in this step here. I've converted this to centimeters. Hope the steps are clear now. Both Varun Kumar and Varun Yadav.
Yeah.
Okay. Same thing you have to do when you use the relation for the phase constant also. Make sure that x naught and v naught are in the same units. So if x naught is in centimeter, v naught should be expressed in centimeters per second. Or basically you can see that this is tan inverse of x naught divided by v naught by omega. So that numerator and denominator should be in the same unit, either both in meters or both in centimeters. So now you'll understand quite easily. So this is the amplitude. Now for the phase constant, so x naught is 6 centimeters plus 6 centimeters and v naught by omega is minus 6 root 3 centimeters. So that is so tan inverse of minus 1 by root 3. So that means tan phi is minus 1 by root 3. So we know that tan of pi by 6 or 30 degrees is 1 by root 3. Therefore, tan of pi minus pi by 6 is minus 1 by root 3, or tan of 150 degrees, because tan of 30 degrees is 1 by root 3. Okay. So that is what will tell us here that phi is pi by 6 radians or 150 degrees. Okay, people, so hope this part is clear. So now once we've got the amplitude and the phase constant, so now we know that for this SHM, amplitude is 12 centimeters. Okay. Phase constant is 5 pi by 6, and omega was given to us as 10 radians per second. The question itself. Okay. So from that we can see that equation of SHM that x is equal to a, which is 12, sine omega t, which is 10t, plus phi, which is 5 pi by 6. So in this equation, x is in centimeters, okay, because that's 12 centimeters the amplitude, and time is in seconds because omega is in radians per second. So once we know this, now we can understand that the graph of the simple harmonic motion will look something like this. So this is positive of the amplitude, this is negative of the amplitude. Now see a general sine graph, how it looks like. It looks like this. This is this type of graph. Okay. Now here what is happening? Initially, what was the value of x naught? It was plus 6 centimeters. Okay. And what was the value of v naught? It was minus 6 root 3 centimeters per second. Okay. So that means it should be at a by 2. So either this point or this point, but the velocity is negative. So it should be coming back to the mean position. So at this point, we can see the velocity is negative because the slope is negative. Because at this point, you can see the velocity is positive. That means this should be my starting point in the SHM. So the graph should look like this, as if this point is shifted to the origin at t equal to 0. This is what the SHM will look like. Starting from a by 2, but having a negative velocity. It's coming back to the mean position, because the velocity is negative. So it's coming back to x equal to 0 at that time. So this is the graph of x is equal to a sine omega t plus 5 pi by 6. That's how we've transformed omega t to omega t plus 5 pi by 6. So there we are. No? Phase constant is there in the graph. So this graph you can see satisfies this condition. Satisfies the condition that x naught is equal to plus a by 2. Is plus 6 centimeters. And v naught is minus of a omega root 3 by 2, or minus 6 root 3 centimeters per second. Understood now, Rahil, how this is different from the standard sine omega t graph, how the phase constant has been brought into the picture. See the difference between the graph of a sine omega t and the graph of a sine omega t plus 5 pi by 6. The starting point has got shifted now. Is it clear, Rahil? आई यूज द फेस कांस्टेंट ना बेटा, तभी तो ग्राफ देखो कहाँ से स्टार्ट हो रहा है, a/2 से स्टार्ट हो रहा है, बिकॉज फेस कांस्टेंट का वैल्यू 5π/6 है ना. सो x0 का वैल्यू जो a/2 है, that is because of the phase constant being 5π/6 na? And why it is starting from this second point over here where the slope is negative rather than this point where the slope is positive, because v0 is negative. Understood now? So that is what the phase constant determines actually, where the graph starts from. Good. Okay. So this type of question, it is called the question involving kinematics of SHM, because we are dealing with things like velocity, displacement, things like this. Okay. So anyhow, let's look at another example. An SHM along the x-axis with the mean position at x equal to 0 has an amplitude of 10 centimeters and frequency of 4 hertz. Okay. At t equal to 0, it starts from x equal to -5√3 centimeters, moving towards the mean position. So first of all, find the phase constant omega and time period, this SHM. Write the equation of SHM. Initial velocity, because that is okay, and also determine the maximum speed and maximum acceleration for this SHM. So this is like a complete question with all the various different type of kinematical parameters that you can be asked in this question. Just try this out. Okay, people. So got a lot of people sending me the answers. Very good. So let me just verify the question. So you can see that first part, amplitude is given to us as 10 centimeters. Okay. And the initial position is given as minus 5√3 centimeters. And the initial velocity will be in which direction? It will be positive. How I know it is positive? Because just visualize the motion. It is given to me that it's starting from a negative point. Okay. So this is our mean position. This is our minus A. This is our plus A. Now where it is starting from, you can see x naught is minus √3/2A. It is starting from some negative position like this over here. But it is moving towards the mean position. Okay. It's given that moving towards the mean position. So that means V naught is in this direction. I don't know the value of V naught, but I know that it is positive. Okay, so that's how I know that V naught is positive. So now you can see that we can get the phase constant from this concept that x naught is A sine phi and V naught is A omega cos phi. Okay, so if x is equal to also given to us is the phase constant, the frequency. So this tells us that omega is 8 pi radians per second, and time period is 0.25 seconds. Okay, so these are two other important things. Now from this you can see this is the case. Now it is given to us that x naught is how much? Minus √3/2A. Okay. And V naught is negative. So this tells me that, sorry, is positive. Okay, that sine phi is minus √3/2, but cos phi is positive. So phi is in which quadrant now? Sine is negative and cos is positive. That means phi is in fourth quadrant. So we know that sine pi/3 is √3/2. So sine of minus pi/3 will be minus √3/2, and cos of minus pi/3 it's plus half. So from that we know that the phase constant phi should be how much? Minus pi/3. So now we know the equation of SHM. X is equal to 10 sine 8 pi t minus pi/3. This should be our equation of SHM.
Sir,
Yes. Yes, beta.
sir, I found out the initial velocity from that formula of amplitude, and then I substituted it in the formula for phi.
That's
From
also okay.
that,
You would have got the
from
same
that,
value of phi. Huh?
no, but I'm getting 2 pi/3.
No, because then see, you have not considered that sine phi is negative. Na? See, tan inverse negative आना चाहिए ना, और नेगेटिव आ रहा है तो सेकंड क्वाड्रेंट में नहीं होगा because cos नेगेटिव और sin पॉजिटिव है. You understanding ना? You must have got it as tan inverse of minus √3, right?
Yes,
ऐसा
sir.
है. Okay. Now see, this has two solutions. Now it has a quadrant 2 solution, which is 2 pi/3, Okay. But this also has a quadrant 4 solution, which is minus pi by 3, because tan is negative in both the quadrants. Now, which of these two we will select? So this is where we understand that here what is happening. V naught is negative. V naught is positive and X naught is negative. That means cos phi should be positive and sine phi should be negative. So which quadrant it is then? It's fourth quadrant, not the second quadrant. Understood, na?
Yes.
So your method is also correct, but you have to just take care that there are, for tan inverse of a negative quantity, there are actually two solutions possible in second and fourth quadrant. So how to understand which of them is happening? So for that, again, you have to see that which one is positive and which one is negative, whether initial velocity is positive and initial position is negative or vice versa. Okay. So this is what our equation of SHM is looking like. Okay. And now rest of the things are formula based. Okay. Equation of SHM ho gaya. Now initial velocity, you can see from this you will get velocity as a function of time will become a omega. So that is 80 pi cos omega t plus phi in centimeters per second. So from this you can see that the initial velocity is 80 pi cos of minus pi by 3 Now cos is positive in fourth quadrant, so it's the same thing as cos pi by 3, which is plus half. So plus of 40 pi centimeters per second, that is the initial velocity. So I've got all these things now. Now what else we need to calculate? Equation of SHM is done, phase constant, all this is done. Maximum speed, and so that is now formula based. Okay. So from this you can also see that third part. Okay. Now fourth part, meters per second, and maximum acceleration's magnitude is a omega square. So that will be 640 pi square in centimeters per second square. Now you can take pi square as approximately 10. So this will approximately become 64 meters per second square. So very high maximum acceleration. Okay. So these two are the answers for the maximum speed and the maximum acceleration. I mean, this is the accurate answer. This is an approximation. So very good. Number if you have got these answers correct. So the phase constant thing was the only slightly tricky thing. Rest of the things were more or less formula based. Okay. Okay, people. So hope this question is clear. So now with this, we move on from kinematics of SHM type of situation. Achha, before that, one more thing we will discuss. An easy way to visualize SHM. Okay. That is SHM visualized as a projection of a uniform circular motion. So if you consider a particle moving about uniformly on this circle, which is, let's say, in the XY plane, then when you look at the shadow or the projection of the particle on either the x-axis or the y-axis, you will see that that is nothing but an SHM. Suppose we have a particle which is going around at a constant angular speed omega. So at any point of time, position vector is like this. So if the radius of the circle is equal to capital A, then at any time, so as this moves, let's say this is the position at time t equal to 0. So this angle is phi. Now after some time, this particle would have moved from here to this position. So let's say it's here now at time t. So from 0 to t, how much angular displacement theta it will have? That angular displacement theta, you can write that as delta theta, whatever. So that angular displacement will be omega t from t equal to 0, t equal to t. So now you can see that at the instantaneous time t, the projections on the x and y axis are x will be equal to a cos of this whole angle now from here to here. This angle theta. So theta is how much? Theta is the initial angle phi plus delta theta, the angular displacement. So theta at time t phi plus omega t. Whereas at t equal to 0, the angular position is equal to phi. So at some general time t, given by a cos omega t plus phi, and y is given by a sine omega t plus phi. So these are both SHMs with omega equal to 2 pi f and pi by 2 phase difference. So as you imagine this particle going round and round in circular path, whichever shadow you're tracing, whether it's the one on the y-axis or the one on the x-axis, you can see that it will be doing an SHM. If you actually imagine a particle like this going around in circular motion, and you imagine that a shadow it is casting on one of these axes, whichever one you select. So when it is here, for example, the projection is at this point. So as it is going like this, the projection is going up. By the time it reaches here, the projection is here, going up. Okay. Then by the time it reaches somewhere here, going like this. So the projection has come back down over here. It's on its way down. By the time it crosses this point, the projection is at the mean position. And it goes like this. So it's doing SHM along the y-axis, you can see. And that is given by this equation. This is an easy way to understand the initial phase also. It's an easy trick to solve for the initial phase in a question like the previous question we are doing. Basically, at t equal to 0, the position of the particle is at t equal to t, the position of the particle is so from this you can see that individually both the projections on the x and y axis they are SHMs. Okay, so let's see how we can use this concept to solve the previous question's phase constant. Okay. It's very effective. See, in that question, it was given that our initial position was minus a by 2 and our initial velocity was positive. Okay. So if we write x as e sine omega t plus 5, only thing is you have to remember that when we write it as sine, you have to consider the vertical axis. So in this case, I'll just take the vertical axis as my x-axis. It doesn't matter what I name it. Okay. And the horizontal axis can be a y-axis or z-axis or whatever. It doesn't matter. So this is my vertical axis. Okay. And the particle is going around like this in omega. So if the initial position is minus a by 2, so this is my minus a by 2. So it means that the particle in its circular motion would be at either of these two places. But at the same time, what is given that the velocity is positive. So that means at t equal to 0, the projection should be here and should be going up. I can see that if it's here, it will not be going up. The projection would be going down. So it won't be this. If it is here, it's going up. So it will be this one. Okay. So this is the position at t equal to 0. This is where it is at t equal to 0. So in general, after some time, let's say it's over here. So at time t, if it is here, then this angle is omega t. So this is our phase constant. This is our phi. So you can see that sine phi is minus half and phi is in fourth quadrant. Therefore, phi is oh, it was minus. Anyway, so I've taken a different example where it's minus a by 2. So this equation of SHM will become x is equal to a sine omega t minus pi by 6. So our x naught will be minus a by 2 and our v naught will be plus root 3 by 2 a omega. In that question, this was actually root 3 by 2 with a minus sign. X naught was minus a root 3 by 2 and v naught was plus a omega by 2, but this is. So this is the usefulness of this projection of UCM method, okay, in kinematics type of questions. Okay, so hope this concept is clear to all of you. Now from this we move on to dynamics of SHM. So basically we've already discussed what equation we use. X is equal to a sine omega t plus phi. This implies that d2x by dt square is minus omega square x. Already implies this. So that means that the net force should become of the type okay, where k is equal to m omega square. So this is a condition for SHM. Okay, that is the magnitude of the net force should be proportional to x. and direction opposite. So any system which has this property, so any system that satisfies the above condition will be an SHM. Okay. With omega square equal to k by m, so time period equal to 2 pi by omega, and x. So these are the important equations. Okay, how to get the value of time period from the force constant k and the mass m of the particle doing SHM, and how to calculate the amplitude and phase constant from the initial conditions, that is x naught and v naught. So this is what we have to learn to apply in numerical problems, okay, when we are dealing with the dynamics of SHM. Just make a note of this section first. Okay, people. So let us understand this in the most simple dynamical example of SHM, which is SHM of a spring mass system. So the first example we will look at of a spring mass system is horizontal SHM of a block attached to a spring. The spring could be attached on either side. So this is a smooth surface. Now let us say this is the natural length of the spring. So from this position, if we shift the block to either here or here, whichever side we are giving the displacement, we can see that the spring will apply a restorative force. If we give a displacement like this, then the spring will develop an extension. So it will apply a force which is inwards like this. So it will have an acceleration which is opposite. Okay. Whereas on the other hand, if given the displacement, this direction, the spring has developed a compression. It will apply a restorative force which is outwards. It will give an expression like this. So both the situations you can see that Kx is equal to ma and A is equal to minus of d2x by dt square, because E is opposite the displacement x. So combining the equation, so this is net force is equal to mass into acceleration. So net force. Okay. So combining these two equations, you can see that we'll get the equation of SHM. Where omega square is k by m, where k is the spring constant, m is the mass of the block. So further from here, time period will become for example, if the spring constant is, let us say, 4 newtons per centimeter, and the mass of the block is, let's say, 1 kg, then the time period will become, we have to convert this to SI unit. Okay, that is, get the time period in seconds. Okay. So this is the fundamental or the simple example of a spring mass system doing SHM when it is kept on a horizontal surface and displaced from its mean position. So you can see that this is the mean position. So whether you give it a positive displacement or a negative displacement, it will have an acceleration which is opposite to displacement and proportionate in magnitude, given by this formula. d2x by dt square is minus k by m into x. So if you compare this with the standard SHM formula, this is standard SHM condition. So not only it satisfies that condition, now you know the value of omega square from the given value of spring constant and m. From that we can calculate the time period. Okay. So with this you can get started with questions based on dynamics of SHM. Okay. Spring mass systems, you can start doing questions along with kinematics of SHM type questions before that. That's it for today's session, people. Wish you all the best and thanks for attending. Have a nice day.